And we're almost live on YouTube. Just a few more seconds.
So everyone has to smile now.
Yes. Don't pick your nose. We're live on the internet.
There we go.
Okay, so welcome everyone. I can see that the number of people joining the conference is sort of climbing every few seconds. So I suppose as I'm speaking, various people will be able to hear bits and pieces of what I say. Welcome to this afternoon's session. Thank you for everyone who contributed and interacted with this morning's sessions. We're still learning how this all goes, so bear with us as we work out the kinks. My name's Andrew Brown. I'm going to chair this session. Originally advertised in the session, we had 3 talks. Unfortunately, Alexandra Lao Castro is unwell, so she won't be able to give her talk this afternoon, but we still have Nina Roellinger and Robin Santra who are going to speak this afternoon. We're going to try something a little bit different with the questions after this session. So whereas earlier on today, we were just using the sort of text functionality in the Q&A part on Zoom, in order to try and encourage a little bit more interaction, and maybe just as a test, since we only have 2 talks in this session, if you have a question that you would rather ask live, as in you want to connect to the camera and ask your question over the microphone, then you can do that by raising your hand. So there should be an option on Zoom to raise your hand. And if you do that, then when it comes to the question time at the end, then we will unmute and enable your camera. And if you can be ready then to ask your question, and maybe it will then allow a little bit more back and forth between the speakers and the people asking questions. The option's still there to ask questions in the Q&A text entry as well, so you can put questions in there too. Hopefully we have worked out some of the technical kinks with people being able to see the questions. I know that some people had that issue this morning as well, and not being able to see the questions that were posed. So we've changed a couple of settings in there, and hopefully that should be resolved. There's still lots of active discussion going on Slack. So if you do have questions in this session that you want to pose to either of our speakers or anybody from the battle or talk this morning, please do go into the relevant channel on Slack and ask your questions there, to try and keep the discussion going and see some interesting ideas coming out there. So without further ado, then we'll move to our first speaker, who has asked me to tell her how many people she's speaking to. So I can see currently we have 66 people in the Zoom chat at present. So that's the size of the auditorium you're addressing. So first up, we have Nina Roellinger, and she's going to be speaking to us about the role of dield coherence and collisions in collective spontaneous emission of FEL irradiated clusters. So over to you, Nina.
Okay, thank you for the introduction. I will now try to share my screen. And I think I have to go into the presentation of the slideshow here. So you should be able now to see my screen. I slightly changed the scope of my topic. I mean, I will give you a kind of overview of the many different theories to treat collective spontaneous emission, that in order to really have a quantitative comparison of theory and our recent experiments. I would like to thank my 2 colleagues, Andrei Benediktovic and Stasis Čučurka, who are working on the theory side of this project. And the experiments, I mean, have been involving several more people, but the main players at the experimental side are Laurent Mercadier, Jose Crespo, and Daniela Rupp. So we had the theoretical work was mainly encouraged by a series of experiments that we have been conducting in the last 10 years at free electron lasers, where we irradiated optically thick samples, mostly gas phase samples, but recently also solids and liquids. We irradiated them with highly focused FEL pulses of a few femtosecond durations, and looked into laser-like emission out of these irradiated atoms. And we're trying to understand phenomena of amplified spontaneous emission, superfluorescence, and inner shell X-ray lasing. And here you can see a typical outcome of such experiment. This was a were 2 experimental campaigns at Flash Free Electron Laser in Hamburg, where we irradiated xenon atoms. We focused FEL pulses that have been tuned above the 4D ionization edge of xenon. And in a macroscopic ensemble of atoms, created a population inversion in xenon 2+ ions. And we observed several strong laser-like emission lines containing something like 10 to the 6 or 10 to the 7 photons in each emission line. And you see here as a function the emission yield, the number of detected photons as a function of FEL pulse energy. So by increasing the pulse energy by a factor of 3, we actually have 3 to 4 orders of magnitude higher signal strength. So it's a quite impressive phenomenon. And if you switch from gas phase to clusters, decoherence in the system starts to play a significant role. Most of you know that if we irradiate clusters with high intensity pulses, we're creating a nanoplasma that evolves on a picosecond, femtosecond to actually nanosecond time range. And these collisions in this nanoplasma then really alter the population dynamics of the system. And you see that the cluster emission is several order of magnitudes lower. And we wanted to have a theoretical approach that would be able to describe both of these systems or at least these decoherent systems or high decoherent emissions on equal footing. In other words, we want to have an approach that goes from amplified spontaneous emission to superfluorescence and superradiance within one coherent approach. So this concept of collective spontaneous emission and superradiance was introduced in 1954 by Dicke, and then it was a quite academic paper where he considered an ensemble of atoms that have been regional in space, small compared to the emission wavelength of these 2-level atoms. And he started out with these atoms in a very symmetric state of excited atoms. So all of these N atoms are in an excited state. And then at some point in time, one of these atoms would decay. And since these atoms are indistinguishable, the state following the decay is a highly symmetric state. That's a coherent superposition of states that can be characterized by N-1 atoms in the excited level and 1 atom that is in the ground state. And he showed by an angular momentum algebra, this highly symmetric Dicke states can be mapped to this angular momentum algebra, that the emission characteristics of this ensemble of our states is very different to the usual Wigner-Weisskopf decay, so this exponential decay and emission characteristics. So super radiance and superfluorescence is characterized by a delayed emission. And this was observed for the first time in 1973 in a dense ensemble of dense and long ensemble of atoms. You see here this intensity profile as a function of time. You have a delayed emission and a peaked emission. This emission peak, it's a very strong peak. It scales with the number of atoms in the sample squared. So it scales quadratically. And it fluctuates from shot to shot. So this delay time, also this peak and this intensity profiles fluctuate from shot to shot. And that's a manifestation of quantum fluctuations on a macroscopic level. And that was one of the reasons why quantum people dealing with quantum optics were very interested in this phenomenon because of this macroscopic manifestation of quantum fluctuations. And the theoretical descriptions, theoretically it's quite a tough problem, especially if one goes to optically thick samples where the propagation of the field needs to be taken into account. And these theoretical descriptions have been mainly based on Maxwell-Bloch equations. So these are, for two-level atoms, one would treat the atomic system as optical Bloch equations, describing the density matrix of the atomic system, and couple these equations to the Maxwell equation for the propagation of light. And in order to account for the quantum fluctuations that initiate this decay process, one either would choose statistical initial conditions in the density matrix, that's the so-called tipping angle approach, or one would use phenomenological noise terms added to the Maxwell's equation or the Bloch equations. And we then realized by looking into the details of that actually these Maxwell-Bloch equations with these phenomenological noise terms they don't describe this transition from spontaneous emission to amplified spontaneous emission to superradiance correctly. One needs basically to go beyond this tipping angle approach, this statistical initial condition approach, because in real experiments, one needs to treat the pump process. Whereas in most of the theoretical treatments, one kind of assumes that one has an ensemble of states already in a certain prepared initial state. And we wanted to really look into the complex pump process to prepare this occupation inverted state in the systems. So for the first method we developed is for a two-level atom, and we start out in the usual way. We treat this two-level atom by matrices that are corresponding to the population inversion in the system and the coherence of the density matrix or the transition operators. And we look into the electromagnetic field is quantized by the usual quantization procedure, treating many different modes. The atom field interaction Hamiltonian is the usual minimal coupling Hamiltonian in dipole approximation. I don't know, I cannot. Okay. Sorry, I couldn't forward my slides. So then we start out to formulate the operator equation. So the Heisenberg equation of motion for these operators, for the sigma operators and the bosonic operators for the field, and formally integrate the expression to get an expression of the time-dependent field operator. And here you see, this formal integration, you get a coupling to the radiation by the atoms, and you are left out with this operator, annihilation operator at time 0. And that's the operator that will account for quantum fluctuations. And then having this field evolution of the operators, you then can formulate the operator equations for the atomic subsystems, so for the population inversion and for the coherences. And one sees that one has terms that still have contributions of this annihilation operator of the fields. These are the so-called Langevin terms. And these are the terms that are capturing the quantum noise that initiates the process. I'm not sure what happens with my slideshow. I cannot. It always jumps around. Sorry for that. And now it's back.
It may be playing automatically timed slides. So if you exit this display mode. Yeah,
I don't know. It was kind of swiping with my mouse, so I don't know.
Oh, okay.
Okay. So this is these are the equations for this Heisenberg-Langevin for the operator equations. And now we are aiming towards getting a mean field description of the system. This means that we would like to recover, the mean irradiated intensity as a function of time, and the mean, the averaged spectral properties of the immediate radiation. So in order to do that, what we need to do is to calculate the mean values of certain correlation functions of the system. So for instance, we are looking into, an equation of motion of the correlation function that measures the coherences of atoms at different spaces points in time in space. So we have here this quantity here is the coherence of atom A correlated to the coherence of atom B at the same point in time. So this quantity then will directly relate to the irradiated intensity of the emission. So out of this quantity, we can calculate the vector potential of the field. And the evolution of this expectation value is given by this equation. And it's almost a closed set of equation, but one actually sees here that here a 3-operator average, ensemble average comes into play. So, one in principle, one does not get a closed system of equations. One would now need to formulate the time dependence of this triple product correlation function. But here now we approximate this correlation function by a factorization and factorize it in 2 terms. So that's quite a critical step in this approximation. And we will see further that this works well for the 2-level atom, but brings along problems for n-level atoms. One can then also go to a continuous description of the medium by not looking into particular atoms A and B, but really performing a swept coarse-grained average over space. Then one gets a function that counts for the population inversion in continuous function as a function of Z, position and time, and a correlation function of the coherences. And these are the resulting equations one can then solve completely deterministically for the occupation inversion and the correlation function. Here we have the radiative coupling terms to other atoms involved. That's sort of follows causally the emission of all the other atoms. And we have here source term for spontaneous emission. And if one gets these quantities, one can then directly calculate the intensity as a function of space and time. And for the spectrum, the emitted spectrum, one needs another correlation function. Via Wiener-Khinchin theorem, we need the correlation function of the potential, the vector potential at different points in time. So we get another equation that we can solve once we have solved the equations of the atomic system and calculate the spectral features of the emitted radiation. So this is this theory presented is quite ideal because we have not treated the pump process yet and decoherence processes. The pump processes can be quite involved, and I am showing here the case for our experiment on xenon atoms, where we started out from xenon in the ground state. This state would be ionized by the FeL to the 4D whole state of the xenon ion. These states would decay via Auger decay to a set of states in the decationic ion. And these same states can also be occupied by direct valence double ionization pathways. So all these pumping processes need to be accounted for in order to really get a quantitative description of the process of emission. And we do this by rate equation approaches. And in the case of clusters, we need to also treat for decoherence effects. And this is technically done by introducing into the Liouville von Neumann equation a Lindblad superoperator acting on the density matrix. And here you can see the Lindblad superoperator for a typical decoherence with a rate gamma here. And as you would expect, from phenomenological theories, typically, what this Lindbladian actually results into is that This correlation function, they do not then decay via the spontaneous decay rate, but by the total decoherence rate, which is the sum over the spontaneous and the decoherence rate. So this is the formal explanation or derivation why we can kind of introduce this total dephasing or decay rates in the system. So now if we solve this system of equations then numerically, here for ideally pumped systems, we can get, for instance, the temporal intensity profiles of the emission and the spectrum of the emission as a function of different interaction length in the systems. So we can walk into through different regions in this elongated system, or increase the optical length of the system, and then follow the emission features. So for very optically thin samples, we recover spontaneous emission. You see here an exponential decay and an intensity profile that's exponential. In the spectral domain, we get a Lorentzian with the width corresponding to the spontaneous lifetime width of the transition. If we go into longer samples, if we increase the optical density in the sample, we then see that at later, points, we have emission that is delayed in time. And so we have the super radiant emission. The total emission yield, here that's shown here, as a function of propagation distance, is increasing, not quite exponential, it's sub-exponential increase, but increases over many orders of magnitude. So we get all this amplification behavior. And if we have very saturated emission, for very long samples, we get this typical ringing phenomenon of superradiance reflected in this kind of peaked structure in the emission. So now if we include dephasing, we see the phenomenon of amplified spontaneous emission initially. So initially we have a much broader emission width that's given by the total decoherence time. And then, the system starts to amplify. This amplified spontaneous emission amplifies exponentially. And in this exponential phase, one actually sees some gain narrowing, meaning that the spectrum is getting narrower and narrower. And at some point, one then transitions to the scheme of superfluorescence, where one again can have this ringing phenomenon. And even in that case, at some point, coherent pulses are created. And we can then really also include the pumping processes and compare quantitatively to our experiments. And here is shown typical gain curves, meaning the collected number of phonons as a function of pulse energy or as a function of pressure of the gas medium. And you see that, we can almost quantitatively describe with a theory the experimental findings. And we have experimentally also measured an increase of the width of the emission that also can be recovered by a theory and supports assumption that we have superfluorescence observed in these xenon emission experiments. We have had recent experiments based on liquid phase manganese salts in solution in water. And we are in the future planning for realizing an X-ray laser oscillator. This is a project in collaboration with Claudio Pellegrini and Uwe Bergmann from LCLS. And here we need to treat at least 8-level system or generalized n-level system in looking into the emission, the super radiant emission of kappa K alpha on the kappa K alpha transitions. And you see that you have to degenerate K-shell levels and 8 final state levels of the different fine structure components in kappa. So the question is, can we use this correlation function approach, and we can immediately, immediately we came up with a 3-level system that showed that this correlation function approach breaks down. So if you consider this degenerate lambda system where you have 2 degenerate ground states of with orthogonal coupling matrix elements to this excited state, you see that you actually need to treat 3 operator correlation functions and even 4 operator correlation functions in this treatment. So for the 4 operator correlation functions, we were quite confident in just splitting them up in factorizing them. But if you actually try to factorize this 3 operator correlation function, you see that due to the symmetry reasons, for this particular example, you see that this correlation function would, in this approximation, be 0. And if you then solve for these mean field equations, what you actually see is that you observe occupations of the excited state that are negative. So completely unphysical results, and that show that the system breaks down. And for n-level systems, I mean, you run into similar problems, and a quantitative description of the emission is no longer possible. So one needs to go to a different approach. And so we opted to derive itostochastic differential equations that are based on Fokker-Planck equations one can derive for this system. I'm not sure if you're familiar or still remember your quantum optics courses. I mean, typically, Fokker-Planck equations might have been covered there. One starts out with the Liouville-van Neumann equations with Lindblad operators, and that governs the dynamics of the system. And then one chooses a representation of the density matrix of the complete system. In the case of superfluorescence, this means we need to treat the combined systems of field and atoms. And we do this by generalized Glauber P function and by representation of this density matrix by coherent states. So this would be, I mean, the first approach one tries, because that's the typical standard approach in quantum optics, to represent the density matrix by a coherent state representation. It turns out that this presentation actually does not work for the case of superfluorescence. The resulting stochastic differential equations we get there are completely diverging. We cannot even describe the decay of a single atom in this case, let alone a super-radiant peak. One would need to average over many trajectories. I mean, basically a convergence of this sampling is very, very difficult. So we introduced a novel representation of this density matrix. And this representation comes along with a second quantization in Liouville space. So that's a quite novel concept that we introduce. We are about publishing a paper on that quantization approach. It's, I mean, you know, second quantization in Hilbert space, but here now we need to quantize Liouville space, the space of the density matrix. That's formally done by introducing creation and annihilation operators with 2 indices. And it will turn out that these trajectories, or this, I mean, that will be come out of this stochastic trajectory approach, that this kind of annihilation operators will play the role of the density matrix, the atomic density matrix. As operators, you can think, I mean, if you have a large ensemble of atoms in a specific region, by this creation operator, we can either create a population or a coherence at this specific site. So you can somehow count correlations and occupations of different atoms. Formally, we then introduce a representation of the density matrix by a quasi-probability function that's made up out of a distribution of delta functions in these operators. And I mean, we can then in this way derive equations, the equation of motion for this quasi-probability function, which has the form of a usual Fokker-Planck equation. I mean, it's written here quite nicely with a partial derivative of xi. You need to know that xi is basically an n-dimensional trajectory where we cover all the different field modes and atoms in the system. So it's actually quite involved. But nevertheless, I mean, formally then we can solve this evolution of this probabilistic distribution function by sampling trajectories. This is given by a classical part of this trajectory and quantum noise part that sort of recovers the quantum properties of the field. And then we can create, I mean, the average, I mean, the expectation value of the density matrix is then just recovered by averaging over these trajectories. So that's the equations in compact form. One can then also rewrite them in a form that sort of then shows is closer to the observables and to the physical properties we actually know. We need to define initial conditions for the bosonic operators and for these trajectories. So we suppose that we initially have no correlations of the atoms in the different regions, and suppose that we have all atoms in an excited state initially. And then one sees that this quantity B that's related to the annihilation operator is actually nothing can be interpreted as a density matrix of the system. And we end up with equations that are very similar to the Maxwell-Bloch equations, but now with noise terms, with derived noise terms that have well-defined statistical properties and that recover the quantumness of the system. So we have here this evolution of the density matrix then that's given by this kind of density matrix, that's given by terms that describe pumping, dephasing, and spontaneous emission. The interaction with the field, here is the vector potential of the field, and features these quantum properties. We have then also an equation, I mean, for the currents that create the fields, and the noise terms between in this currents and in this simple density matrix description, they are correlated. I mean, so that you see that that's the kind of correlation of the noise properties we need to realize. And we actually, I mean, it's more an art than real that we can give a really good description how to get these noise representations. But for large number of atoms in the systems, for n larger than one, much larger than one, we really can solve these stochastic differential equations, and they turn out to be stable. And here I'm showing you first results of kappa on the kappa k alpha transmission in this 8 level atomic system. You see here, for instance, populations, the average populations of these two states, final states, averaged over 100 runs. I mean, at some point they should converge to one line, so they should be equal by symmetry reasons. So you see that we are not quite yet converged, and the coherence. The coherence, I mean, it's reflected. I mean, for a single trajectory, is actually quite large and reflects the emission of the super-radiant emission. But on average, I mean, the coherence has to be 0. So this is a kind of a convergence check for the trajectories you would for your trajectory ensemble trajectory approach. We can then also get single trajectories for the temporal emission profiles or average temporal emission profiles and the spectrum. And I would just like to mention that this kind of trajectory approach is very appealing, because if we have the stochastic trajectories, we can calculate higher order correlation functions of the immediate fields and distribution functions of the field properties that we can directly compare to the experiment. For instance, in the experiment, we have here the number of photons compared as a function of pulse energy. And if one looks experimentally in the distribution of photon numbers at a given pulse energy, one sees that this distribution changes quite dramatically, from exponential decay-like to a kind of log normal distribution or something. So I mean, we can now we have a theoretical means of really predicting these distributions now by this trajectory approach. So as a summary, I introduced a mean field approach to treat superfluorescence by coming up with the equation of motions for the 2-point correlation functions of atomic coherences. It works well for 2-level systems, but in order to treat these systems in a computational tractable way, one needs to factorize 3 and higher order correlation functions, and this factorization is no longer possible for n-level systems. So we introduced a new itostochastic differential equations approach. We could show, that is introduced based on a novel second quantization procedure of Liouville space. We basically derived stochastic differential equations. Were successful in constructing the appropriate noise terms for these differential equations, and showed first successful application to the kappa k alpha emission. For 0D, for the 0D case, meaning that we did not treat any propagation of the fields yet. And in the future, we are going to implement this itostochastic differential equation approach into 3 dimensions. And the first application will be really a project that's planned at LCLS to realize the first X-ray laser oscillator. And with this, I thank you for your attention, and I'm open for questions.
Okay, thank you very much, Nina. That was really fascinating stuff. So we're up to 84 people attending who can ask questions. So as discussed at the start, if you have a question, you can use the raise hand functionality on Zoom, in which case we can enable your microphone and camera to ask a question in person, or you can simply type a question into the question and answer sort of text entry part there. So Henry is going to keep an eye out for anybody who's raising a hand. And while we're waiting for the first question from the audience, perhaps I can ask, so in terms of this outlook, in sort of extending this method that you've described, you mentioned the propagation effect. I mean, how much work is there to extend to look at the propagation effects, and is that sort of built into this 3-dimensional method you're proposing to?
It's numerically going to be very challenging. So it's numerically challenging, and then the big question is if the noise terms will remain stable in this approach. So we have to develop a new strategy. How to do a numerical, full approach. Even on the scale of the Maxwell-Bloch equations, it's quite difficult, because it's a multi-scale approach. One needs to cover basically we have propagation distances in the experiments up to a few millimeters, and one covers a field amplification over 8 to 9 orders of magnitude in these 3 millimeters, and one has to treat quantum noise at the same property. So it's quite it will be quite challenging.
Okay.
Also for the noise operators, to construct the noise, for this simple system, this 8-level system in kappa, this model system, we need something. We have noise matrices of 200 by 20. The matrices are really huge. And we have 64 density matrix elements. And I mean, a couple of, the equations I showed were very complex, compact in the way we wrote them down, but I mean, there are a lot of coupled differential equations. And to really come up with a stable representation, with this noise, is difficult. One has a certain gauge freedom in this noise. So the only thing one has to reproduce are these second order correlation functions of the different noise terms. That's the boundary conditions, but within these boundary conditions, one can play around with choosing different realizations. And different realizations turn out to be stable or unstable in the numerical implementation. And that's something we want to understand in the future. And we also have a collaboration with an applied mathematician here that will start soon in order to look into that from a mathematical point of view.
If your matrices get any bigger, then we're dangerously close to it being an HPC question, a high performance computing question, which starts to pique my interest. Okay,
we will run into that for sure if you want to have a full 3D description of the process.
Okay, there don't seem to be any questions coming through. I'm not sure if that's if my question answer text is frozen, but if there are any questions that you've attempted to get through and haven't been able to get through, you can of course add those to the Slack channel, and there'll hopefully be some opportunity to discuss that after today's session. But for now, thank you again, Nina. And we'll go to our second and final talk of this session, the last talk for today. It's Robin Santra. I realized earlier on, Robin, that you're the first academic I ever heard speak at a conference. So this is a nice recollision effect happening here. We look forward to hearing what you have to say about whole decoherence in attosecond photoionization. Over to you, Robin.
So thank you very much, Andrew, for the introduction, and also thanks to Carla and all the other organizers for inviting me. I'll talk about whole decoherence in attosecond photoionization, and basically I have one slide of introduction. If we ionize an atom or a molecule, and we might be using either a weak one photon or a few photon type process to knock out an electron, or if we use strong field ionization, then the natural question to ask, at least for the attosecond science community, is under what conditions will the state of the whole produced actually be non-stationary? And the answer is obvious to all of you. You will say, well, the state of the whole will be non-stationary as soon as you have a coherent superposition of whole eigenstates, of non-degenerate whole eigenstates. Well, fine, but a more accurate answer, it has to be an at least partially coherent superposition. And if you have a situation where the superposition of the electronic eigenstates is not fully coherent, then you cannot actually use a wave function or a Schrödinger cat to describe such a partially coherent state. You would require a density matrix, right? So I'll be talking a lot about density matrices. And how coherent a whole state that you can produce via photoionization will actually be, this depends. So Nina and I started worrying about this more than 10 years ago in connection with atomic strong field ionization. And what I'm showing you here is a calculation from a paper with Steve Leone and Ferenc Krauss, who looked at the degree of coherence built up through strong field ionization using attosecond transient absorption spectroscopy. But what I'm showing you here on this slide is, in the upper panel, is the time evolution of whole populations. And in the background here in red, you see the time evolution of the strong optical pulse, roughly 4 femtosecond pulse used to strong field ionize the valence shell of krypton. Now the valence shell of krypton, that's a 4p, and you form the ground state if you rip an electron out of what is called the 4p3/2 level. So where the orbital angular momentum of the whole is 3/2. There is a fine structure excited state with an orbital angular momentum of 1/2. And what this figure shows you is that the most probable hole state produced by the end of the pulse corresponds to a hole in the 4p3 halves with an m quantum number of plus or minus 1/2. This level here, which is relatively strongly suppressed, is also a ground state level in this degenerate ground state manifold, also J equals 3/2, but m plus or minus 3/2. So to put it differently, the strong field ionization process forms an ensemble of ions that are strongly aligned. You have a non-uniform distribution of m quantum numbers. But what is relevant for us here when it comes to decoherence is the fact that we have a quite significant population of the spin orbit excited 4p state, the 4p1/2 state. This is the population here for the 4p1/2. And you can have coherence in this particular problem because we're doing strong field ionization with a linearly polarized laser field. You can build up coherence only between this manifold, the 4p3/2 with m plus or minus 1/2, and the 4p1/2 with m plus or minus 1/2. So m is conserved in this problem. This 4p3/2 with m plus or minus 3/2 level has 0 off-diagonal density matrix element. So when I will talk now about the degree of coherence, I mean the off-diagonal density matrix element associated with these two levels. In the lower panel, I'm showing you the time evolution of the degree of coherence for the 4 femtosecond pulse shown up here. And you see that by the time the pulse is over, the density matrix corresponds to a degree of coherence of only about 60%. So strong field ionization, even with such a relatively short pulse, produces not a fully coherent superposition of the whole states. And if an 8 femtosecond pulse had been used, you would end up with something like 10% for the degree of coherence. Now, the 60% degree of coherence that we compute here is consistent with the experimental data, the attosecond transient absorption spectroscopy data that Steve Leone and Ferenc Krauss and collaborators obtained 10 years ago on krypton. So basically what they do is they measure as a function of the delay between the strong field ionizing pulse that produces krypton plus with a hole in the 4p shell and an attosecond pulse that is time delayed and interrogates the hole produced. You see here that you have 3 spectral lines that correspond to exciting an electron from the 3D shell into the 4p hole, right? And the 4p hole can either have a J of 3/2 or a J of 1/2. And basically you see how these absorption lines, they beat in time. That's from the dynamics of the hole. That's because you have actually some degree of partial electronic coherence. And basically from the contrast of these oscillations, one can directly extract from the experimental data the degree of coherence formed in the 4p manifold, and that's 60% just consistent with what I mentioned earlier. Now, this slide tells you that it seems like if you make the pulse shorter than 4 femtoseconds, so if you can squeeze the pulse a little bit more, then you should be able to get to a higher degree of coherence. And that has actually been demonstrated using optical waveform synthesizer techniques to basically get kind of a quasi half-cycle pulse. Then one can get up to about 80%. So that might make you think that the only thing that controls whether you get a high degree of coherence or not is whether you get a really, really short pulse. Well, not necessarily. So what I'll show you now is a situation where we'll simply do 1 photon ionization, but we'll use a much shorter pulse. We'll simply use an XUV pulse. And this particular slide, it's going to be a 20 attosecond pulse. You would think that's pretty short. And we're going to be photoionizing a xenon atom, and we'll be looking at the degree of coherence between the 4D inner shell and 5s inner valence levels, right? So we're taking the short pulse, we're knocking an electron out of the 4D or the 5s, and we want to watch the degree of coherence. And somehow we would think if we do this with a sufficiently short pulse, such that the spectral bandwidth of the pulse is larger than the energy separation between the two levels, then we should have a high degree of coherence. Well, look at this figure. This shows you on the vertical the degree of coherence between the two Hall states. On this axis, tau is the duration of the pulse, and the time axis, that's the time corresponding to the time evolution of the degree of coherence after the ionizing pulse. So the real-time evolution as the electron flies away from the ion. And you can see at very early times your intuitive expectation that if you make your pulse sufficiently short, such that your spectral bandwidth nicely spans the two initial levels that we're considering here, then the degree of coherence simply converges up to 1. But that's not kind of the asymptotic value, because once you now allow the photoelectron to actually fly away, you see the degree of coherence always drops relatively quickly as a function of time. And when you look here at large times, this is 1 femtosecond after the ionizing pulse, and this projected onto this plane, then you see that we actually reach a maximum degree of coherence of 0.6. And as we make the pulse shorter than about 30 attoseconds, then the degree of coherence actually goes down, in contrast to what you might have thought. Well, this shows you that it's not only the pulse duration that controls whether you're actually forming a coherent superposition through photoionization, but there's another effect. And in this particular situation, the physics of why you get this kind of asymptotic decoherence is because the photoelectron that flies away from the photoion, it talks to the different channels of the ion. So you have a correlation effect between the states that the ion can have and the different states that the photoelectron can have. This sort of interaction between ion and photoelectron causes entanglement between the Hall and the photoelectron. And as soon as you have two entangled degrees of freedom, but you're looking only at one of the 2 degrees of freedom, in this case the Hall, then you have basically a mixture. You have lost coherence. You no longer have a pure state for the Hall. And why is this happening as you're making the pulse shorter and shorter? Because a shorter pulse means at fixed mean photon energy that you have relatively low photon energies in your spectral distribution of your XUV pulse. And these low photon energies cause the formation of relatively slow photoelectrons. And these slow photoelectrons, they have a lot of time to interact with the ion, and therefore they cause the decoherence. Now, if you have a short pulse and you want to suppress the decoherence, then the simple solution is make the photoelectrons on average faster, make them go away from the ion quickly enough such that the entanglement between Hall and photoelectron gets suppressed. This is what is shown here, where you see the degree of coherence between 4D and 5S as a function of time after the ionizing attosecond pulse, and the different curves correspond to increasing mean XUV photon energy. And as we increase the photon energy, you see how the asymptotic degree of coherence increases, again, because on average, the photoelectrons leaving the ion behind are faster, and therefore you have less coupling between eigenstates of the ion and states of the photoelectrons. So this suppresses decoherence. Now, I should be honest, there is a third reason why there is decoherence, which we artificially suppressed in the situation. That's connected to the fact that we're considering one photon ionization here. And when we are photoionizing a 5s electron in the dipole approximation, you're creating a p wave for the photoelectron. When you're looking at the 4D and you're photoionizing that in this photon energy regime, then you're producing a p wave, but actually predominantly you're producing an F-wave photoelectron. And because the F-wave is not accessible to the 5s, you actually produce a relatively low degree of coherence in reality. And when we compute the degree of coherence that we show here, we actually remove the F-waves completely from the picture so that we can focus on these common P-wave channels, which can potentially give rise to a high degree of coherence if we manage to suppress this entanglement between electron and Hall. But the selection rules are part of the reason why in physical reality you would have actually, for this situation, a much lower degree of coherence than what is shown here. This motivated us to ask ourselves, can't we actually do something about the degree of coherence? Can't we use quantum optimal control to maximize the coherence of the hole that you produce in the ion? And the example I'm showing you on this slide was a situation where we considered argon, and we wanted to produce a coherent superposition between 3p and 3s holes. This should be more challenging, you would naively think, because with one photon ionization out of the 3s, you go into a p-wave continuum, right? But with one photon ionization out of the 3p, you go into a continuum of opposite parity. So because the two continua have opposite parity, you should have, at least in one photon ionization, absolutely zero coherence between the two. Now, the solution that the control algorithm finds is not entirely surprising, but let me explain it nevertheless. So with the optimized field, you see here the degree of coherence, and you see that it's basically 1 after the pulse is over. This is the red curve. And what we also try to ensure in this optimization, we required the 3p population and the 3s population to be equal to one another, so that you form a 50-50 superposition of two states, so that the diagonal elements have equal weight, and there is a non-trivial, non-zero off-diagonal element. Well, you see that this works really nicely. The dashed line, that's the 3p population. The solid line, that's the 3s population. After the pulse is over, both have a population of about 25% or so in this problem. So we managed to get a decent 50-50 population with a high degree of coherence. When you look carefully at this figure, you also realize what the mechanism is. So essentially, if you look at these ionization potentials here, what the pulse does, what the optimized field does, it uses a photon energy that basically corresponds roughly to the energy difference between the 3p and 3s levels. That's, you see, you have 0.6 atomic units for 3p, 1.3 here for 3s. So the difference between the two is 0.7 atomic units. So with a 0.7 or so atomic unit field, you can photoionize the 3p, but not the 3s. So as you can see here, initially, you're really producing predominantly 3p whole population and not so much 3s whole population. But because you are in resonance with the 3p 3s transition, as soon as you knock an electron out of the 3p orbital, then you can start resonantly exciting an electron from 3s into 3p. And essentially in this way, you manage, through what is a 2-photon process for the 3s and a 1-photon process for the 3p, you manage to produce the necessary coherent superposition with a good, 50-50 weight for the two levels. Well, this looks good, so let's try the same thing for xenon for our 4D 5s superposition. Okay, so we see in the upper panel for the optimized field, the degree of coherence that we managed to achieve for 4D and 5s in xenon goes to about 80%. So that looks encouraging. With the original gas pulse, with a mean photon energy, this is the blue curve shown down here, with a mean photon energy of around 140 eV, taking into consideration that we're photonizing into P and F wave channels, we get an asymptotic degree of coherence of only about 20%. So the optimization really helps us. Interestingly, the optimized spectrum, or the power spectrum of the optimized pulse, has much lower photon energies than average. In particular, the average photon energy here is lower than the 4D threshold. That means, in contrast to what we started with, where you can directly photonize 4D and 5s, our optimized field suppresses 4D ionization. There's no longer any substantial 1-photon ionization out of the 4D. We predominantly photoionize 5p and 5s, and the 4D whole population is generated by 2-photon excitation of a 4D electron into the 5s hole, or alternatively, 3-photon ionization of the 4D. Now, as you might imagine, this causes a problem, because now, since it requires a multiphoton effect for the 4D to become ionized, and the cross-section for the multiphoton inner shell absorption process is not terribly high, the dilemma that we now face is shown here. For argon, we were able to get a nice 50-50 superposition with optimal control. Here, when we have a high degree of coherence between 4D and 5S, say around 80% or so, then you see that the whole population ratio is practically zero. This is shown here in the inset as well. That means you have almost zero population for the 4D, and most of the population is in 5S and in principle also in the 5B. So this is not terribly useful. Yes, you do get a high degree of coherence, but you don't have anything close to 50-50 superposition. So this is a problem, and we don't have a solution for that yet. Now, there is another reason why decoherence can arise, and this refers now to polyatomic systems. You can have electronic decoherence as a consequence of nuclear motion, in particular nuclear zero-point motion. This is something that Mike Robin collaborators had also looked at. What I'm showing you here is a result from our paper from 2017. This shows you not the degree of coherence, but the quantity that's very closely related to it. So we're taking, in this particular figure, phenylalanine, and we're considering exactly two cationic states, two valence hole states, not Rydberg states, the HOMO and HOMO -1 states of phenylalanine. And we're constructing for this nuclear electronic problem the reduced density matrix by tracing over the nuclear degrees of freedom. And this is the matrix rho. Initially, it's a pure state matrix, so rho squared equals rho as long as you're dealing with a pure state. And we're doing a 50-50 superposition of the two cationic states. As a consequence, as soon as there is complete decoherence, the density matrix rho is diagonal with diagonal elements 1/2. And so you have 1/2 for one level, you have 1/2 for the other. When you take rho squared, you get a quarter for one entry and a quarter for the other, and the trace gives you a 1/2. So to make a long story short, what is shown here, even though it's not the degree of coherence, it directly reflects the degree of coherence as you go from a trace of rho squared equal to 1 to a trace of rho squared equal to 0.5. That's when the off-diagonal element of the reduced density matrix of the electronic subsystem is 0. And what you can see is that the degree of coherence as a consequence of all 63 normal modes in phenylalanine has dropped to 0 within about a femtosecond. So you have very, very rapid decoherence in the electronic subsystem, not actually because the nuclei have any time to move, but you have a lot of hydrogen atoms in the system. So you have a certain spatial extension in your neutral ground state for this molecule for the vibration, for the nuclear positions in the system. You're sampling, if you want, a whole range of different nuclear geometries before you're photoionizing. And at these different nuclear geometries, the energy separations between the two cationic states are not constant in the vicinity of the ground state vibrational wave function. So as a consequence, at different points in this nuclear geometry space, you have different phases for the electronic time evolution, and you're basically averaging over that when you're averaging over the nuclear wave function, which is basically, as I said, not a wave function that moves all that much during this short amount of time, but you have enough phase evolution between the electronic states that you get very rapid electronic decoherence. Individual nuclear modes don't necessarily do so much. You can see here the contributions from the 63 individual modes, and some of them cause very little decoherence, but then there are some that individually cause relatively rapid decoherence. And as I said, if we take them all together, within about a femtosecond, the coherence is basically gone. Now, most recently, we tried out the following. We were interested in seeing basically this combined effect in a molecular case of electron-ion interaction together with the nuclear zero-point motion. So what we did here is we looked at the water molecule, And we considered again a 50-50 superposition for a hole in the HOMO and a hole in HOMO -1. And what we did here is a little bit less sophisticated than on the previous slide. We're not actually doing here any quantum wave packet calculation for the nuclei and also not for the photoelectron. But what we're doing here is what is technically called a fewest switches surface hopping calculation. This is a mixed quantum classical calculation where the bound electrons that define the cation, they're still described quantum mechanically. Through individual quantum states, but the motion of the nuclei is described classically and the motion of the photoelectron is described classically. And basically we treat the photoelectron like the nuclei in the framework of this fewest switches surface hopping calculation. And what we see basically as we calculate now, again, the degree of coherence, not trace of rho squared, as a function of time after the attosecond pulse, in this case, you get relatively rapid early decoherence as a consequence of the interaction of the photoelectron with the photoion. So this early entanglement between photoelectron and photoion, and then as a consequence of the nuclear zero-point motion, you get this somewhat slower decoherent, well, I should not say somewhat slower, significantly slower decoherence in comparison to the electronic contribution. What is shown in gray here is if we turn off the electron-photoion interaction and consider only the decoherence from the nuclear zero-point motion. So before showing you my last slide, I'd like to acknowledge Antonia Karamatsko and Carolina Arnold in particular from my group, and also from Christiane Koch's group in Kassel, Esteban Götz, who worked on the optimization calculations. So let me summarize. When you photoionize in any electron system, in general, you do not produce a coherent n-1 electron wave packet. What you really require, instead of using a Schrödinger wave packet, you need to describe this resulting state in terms of a density matrix. And there are a number of reasons why, in general, you require such a density matrix. The most obvious situation is that your pulse is simply not short enough to knock out the electrons so quickly from the various levels involved that you can really kind of beat the phase evolution of these levels individually. Right? So you basically want to have photoionization on time scale that's short in comparison to the time scale defined by the level spacing, by the largest level spacing in your problem. That's a minimum requirement, but unfortunately it's completely insufficient. It can easily happen, and I showed you xenon as an example, that as a consequence of what people might call interchannel coupling, an electron-hole correlation effect, that you basically suppress the degree of coherence. Then in simple situations, like in atomic photoionization, when you're affected by selection rules, it can be that from the different channels, you end up in different continua, and then you have, well, a suppression of coherence or possibly no coherence whatsoever. And last but not least, in polyatomic systems, nuclear motion will, at least in general, lead to electronic decoherence on potentially relatively short time scales. So my main conclusion is that the preparation of long-lived coherent superpositions of non-Rydberg electronic states, so long-lived in the sense of if you want to really kind of use attosecond science to push chemistry on longer time scales, and so such time scales would then have to correspond to time scales beyond a femtosecond. If your goal is to prepare such long-lived coherent superpositions of compact, non-Rydberg electronic states, then it seems generally difficult even for atoms, as I showed you, but particularly challenging for molecules. Thank you very much.
Okay, thank you very much, Robin. I find every time I thought of a question, you answered it in the next 10 seconds after I thought of it. So we have one question in the Q&A already, which I will read out because it's been put in the Q&A, but I'll just remind people, if you want to ask a question in person or over the camera, you can raise your hand and we will enable you to speak. This question from Emilio Pesanti. So for the decoherence of phenylalanine through nuclear motion, if one looks at just the single worst nuclear motion mode, Is it basically equally bad as the combined effect? And can you comment on the nature of that particular mode involved in that channel, as well as the next few worst cases?
Yes, so this situation here, the thing is, what basically causes decoherence is, as I indicated in words, if you're looking along a specific normal mode, and I should say immediately what normal modes I'm referring to here. The normal modes could refer to the neutral ground state, or they could refer to either of the cationic states, right? Because they have their own potential energy surfaces, so you have different sets of normal modes. I'm referring here to the normal modes defined by the ground potential energy surface, because basically we're doing sudden ionization. So we're starting from the ground potential energy surface with the corresponding ground vibrational wave function defined by the ground normal modes. And now we're rapidly removing an electron. And the question is essentially, viewed along each of these ground state normal modes, how quickly do the potential energy surfaces, or more accurately, how quickly does the distance between the two potential energy surfaces vary over the extension of the normal mode of the vibrational wave function along that normal mode. So if you have a vibrational wave function that's relatively strongly delocalized along a certain normal mode, and the corresponding energy differences vary significantly over that range, then that's where you will get the most rapid decoherence from, right? So modes that correspond to relatively small spatial extension of the associated vibrational wave function normally don't lead to much decoherence. So imagine, just as an argument, imagine you took an iodine molecule and you did the same thing in iodine, you would see relatively little decoherence on those timescales because you have only heavy atoms and your nuclear wave function is very strongly localized. Here we have quite a few light atoms. It's an organic molecule after all, and that leads to much more extension in nuclear space than you would obtain if you had only heavy atoms. And this is the main reason why I would think one should expect in general for organic molecules such rapid decoherence effects. For non-Rydberg type states. So if you have a Rydberg type state, and your Rydberg state, is a true Rydberg state so that it's kind of, sufficiently diffused that the electron doesn't really penetrate much into the ion core, then the potential energy surfaces will be nicely parallel and you'll get much longer coherence times. And you will see beatings for a while. But this is very difficult, I would say, for such valence states where the potential energy surfaces are normally not parallel to each other, unless you have a very special situation.
Okay, Emilio has another question. Emilio, we've enabled your microphones. If you want to ask a question, you can go ahead and speak. Perhaps that's not possible. Okay, so for the benefit of anyone who can't read the question in the Q&A.
Sorry, can you hear?
Go on. Yeah, go on ahead, Emilio.
Hi. Sorry, we were watching on YouTube, so I'm delayed.
Yeah, go ahead.
So actually, that's my second question. So in most of your early examples, the coherence is lost into the photoelectron. So normally if you have coherence lost into entanglement, you can recover it using quantum eraser principles. So by suitable coherent measurement of the superposition that's in the system that you're not normally observing, so in this case, a photoelectron, you could in principle recover the coherence. So if in the angular dependence case, this could be as simple as whether the electron goes up or down. So this should be possible with the examples that you described at the start, at least in the angular dependencies.
Well, it should be possible, sure. If you can basically measure everything, you have, of course, recovered the coherence, because then you're just looking at the full thing. And if you're looking at the whole thing, then of course you don't need a density matrix. Then you can recover every coherence in the world. is it realistic? It depends, right? So one point for these old attosecond transient absorption spectroscopy experiments was that they were done with relatively dense gases. So it would have been difficult to measure the photoelectrons together with the ions, and characterizing the full quantum state together with the full quantum state of the whole, and in that sense forming some sort of perfect coincidence measurement will not always be possible. But if it is, you're doing a full measurement on the entire quantum system and you're not losing information, and sure, you would get coherence. Absolutely.
Cool, thanks.
Okay. There's another question from Florian Opperman. So is it possible to enhance coherence in polyatomic systems using optimized fields, for example, by exciting certain normal modes on purpose?
So that's an interesting thought. So we didn't apply any optimal coherence theory to this situation, but in principle, if one could create a superposition that's somehow much more localized in nuclear configuration space, so not a vibrational ground-state wave function, but something where intentionally you form, before you photonize maybe, a superposition that's sufficiently localized in nuclear configuration space, then that might help at least on time scales that are shorter than the true nuclear time evolution scale. Because here we see decoherence on time scales before the nuclei really move in any noticeable fashion. But you could imagine creating something that's more localized in nuclear space, and then as long as you're not waiting too long, you might at least suppress this very rapid early decoherence if you're forming a nuclear wave packet that, as I said, is more localized than the ground-state vibration wave function is. So if you have some way, some sort of shaped IR pulse to create a nuclear vibration wave function, then you suddenly ionize with an attosecond pulse. I think that might work, yes.
Cool. And one other question, and I can see that Henry has enabled your microphone. So Alexis Augustin Chacon Salazar, if you want to ask your question, you can go ahead and ask it. Just unmute your microphone.
Unmute. Okay, do you listen to me?
Yes.
Yes, here my question is just simple. How do you speculate how this decoherence can affect the high harmonic generation emissions? In particular, I mean for the plateau around the cutoff. So would you please explain it in more detail? And I'm a little bit interested or curious about that question because I'm nowadays working more in the line of solid state physics. We have some kind of details of the dephasing time in that directions. Thank you.
Well, so this is a little bit subtle in the. So normally when you do harmonic generation, you're basically going back to the ground state, right? So you're knocking an electron out and you're basically going back to that state. That's the ideal situation of any harmonic generation, right? You're basically not going to an excited state. You're hopefully not exciting anything else. You're just going back to the state you came from. If that's the case, then you're not actually considering an open system. Right, so the situation I talked about was where you're separating basically two systems A and B, and at the end you're looking only at subsystem A, and subsystem B is gone to infinity or whatever, but at least you're not looking at subsystem B. When you're looking at harmonic generation, that's a bit different because in principle you're looking at a closed system, in principle. Right, so I cannot directly apply the sort of I separated the way I did it into A and B. But at the same time, of course, when you're emitting light from a solid, whether you're really always in this ideal situation that you're starting the ground state and going back to the ground state, that's also not necessarily true, right? There may be actually, and whenever that is happening, then of course you're looking again at degrees of freedom that you're not actually involving typically in the modeling, so that one might have too much coherence. And once you allow coupling to those other degrees of freedom, as if you want, as a bath, so to speak, a bit similar to the sort of models that Nina has been talking about in her talk, where she used some sort of Lindblad way of calculating the time evolution of for the density matrix of an open system, then one could treat it that way. But But what I described, the separation between what I consider system, which was the photoion, and what I would consider the bath, which is the electron flying away, was very clear and is in that sense not directly applicable to the HHG scenario.
Okay, then here we don't know exactly what would be.
No, I think this is an interesting problem, obviously, yes, absolutely.
Okay, absolutely open questions. Okay, thank you.
You're welcome.
Very good. Okay, there don't seem to be any more questions popping up in the Q&A. So thank you once again, Robin, for a really fascinating talk. And thank you to Nina as well for her talk earlier on. I believe this is the point at which we're going to close the YouTube live stream. So we have some announcements for the people who are on the Zoom chat. So Henry, you can go ahead and